Okay, excuse me. So let's move on to the next topic. The next topic is also related to this trying to reduce the complexity of problem. Excuse me. You know, even though I hear all the talking, I still hear words like standard deviation and all that. So clearly, you're not talking about movie plans for the night, right? So, we talked about one of the biggest use for the PCA method is dimensionality reduction. Okay, whatever is the machine learning algorithm you choose to do the learning, whether it's a regression problem or classification problem, you want to use some algorithm, and particularly when your original data set has large number of features, running these algorithms sometimes get hard, impracticable, so you go for dimensionality reduction. The way you did this dimensionality reduction was by looking at only x values. Excuse me. Only looking at the x values, not looking at y value. What you did was you took the x value and you did a linear combination in such a way so that and got new set of variables in such a way that the first variable had the most amount of information, second variable has the next level of information, and the last variable had the least amount of information, and ordering it this way allowed you to drop a set of the lower variables and do a easier job of modeling, right? But we did not focus on y. The next method we are going to be talking about talks about is there a way to do it while focusing on y as well. PCA had a big disadvantage in that this new set of variables it gave, although mathematically sound in the sense that first variable had most amount of information, it was very sound mathematically that way, it lacked interpretability because the first variable is some linear combination of the 13. Okay, if we don't like that idea that of losing interpretability, I want a way to cut down dimensions and still maintain interpretability, step AAC was a good choice. Step AAC still kept your original variables in terms of original variables. The only thing is it took a painfully long process. I want to do what step AAC does, and that keep original variables, keep interpretability, but I also want dimensionality reduction. Okay, what do I do? Regularization offers you a way. Okay, but I want dimensionality reduction, but from the concept of from the direction of trying to avoid overfitting or deciding whether we are doing overfitting or underfitting. So this is something that we talked about earlier. We have this bias, this inherent desire to use as simple model as possible to define, to clearly, accurately predict the situation. But by choosing simplicity, often we sacrifice on accuracy. Okay, and so this is always a thing. I mean, are we, by going towards extremely simple model, are we losing accuracy? What is the right level of balance, right? And when you're talking about accuracy, what you really mean is accuracy on the test set, whereas you are doing the model on the train set, right? Your model does gets you some level of accuracy on the train set. On your test set, it might be completely different set of accuracy. And this issue about differences in performance between train set and test set is something that we talked about yesterday. It's worth repeating, so I've copy pasted the same set of slides. What you see here on the x-axis is the level of complexity of the model, some notional level of quantifying the level of complexity in the model. Perhaps it's small number of features to more number of features, or perhaps you are talking about starting from linear polynomial to quadratic to 13th order polynomial. What happens is, when you start with a simplest of models, on your training set you might have value of your the error on the training set might be high. As you increase, going from the complexity of your model, moving from linear to quadratic to cubic to so on, that error in your training set tends to drop. But what happens on your test set is something completely different. As you are increasing the complexity of the model in the train set, initially the test set error will also drop, but soon the test set will start increasing. The error in the test set will start increasing as the complexity of the model is higher and higher, because the training at some point starts fitting even noise in the data. Whereas that noise in the data might not be accurately represented. The noise will be of different type in a test set because it's actually noise. And so the error sizes will become large. Okay. And we talked about how in the side of simplicity, we have a problem of high bias and high value of training and test error, but consistency between training and test error. But as you go towards the overfitting side, you have high variance, low bias but high variance, and there is no consistency between test and train set. I wanted to illustrate this with a concrete example, simple but hopefully concrete example. Here's an example I chose. What you see here is a simple data that I generated with some noise, to you I'm presenting the full data, but the data that is there available for training is represented in black, and the data that was available for test is represented in red, so that you can see how a model that is fitted based on black dots does well when you're thinking about red dots. Okay, is the idea clear? I'm giving you are going to fit a model only on the black dots and measure the error from the red dots based on different models that you do. Yeah. Sorry. Difficult to spot the black and red. Now I know that. Yes, I should. It's very clear on my monitor, but so here are the reds. That's a red. That's a red. I would use the marker, but I might get fired for that. So let me. Yeah, it's hard to improve the contrast on that. So here is the set of this thing. I'm going to do 3 different models: linear, cubic, and a 5th order polynomial. So when I tried to do the linear model on that, it basically decided that more or less a flat line was the best line. So that's the thing you did. So these were the reds. So this is the size of the error on your test set. Okay. So in this case, actually, it's not bad at all. When the error on the test set is not bad, but clearly you can see from the blue line, it doesn't capture the trend in the data. Okay. So this was the train error, and that was the test error. In this case, the test error was actually smaller than train error. That won't always happen. They are typically around the same level of magnitude. When I did the cubic, it seemed to capture the data very well. Okay, and you look at the train error dropped. When in test it was 1.23. When I increased the complexity of the model, the train error dropped to 0.33. Okay, and the test error was also pretty good on this. I went to a 5th order model. When I did the 5th order model, you can see now which ones were the red points and which one are the black points, right? Because it actually fit the black points very well. The train error is 0. It perfectly fit all the black points. But the test error just extremely high. You go to a more and more complex model, it's trying to fit these points exactly, that you might end up losing the overall picture, and you did do really poorly on the test data. What has happened is, as you moved from here to there, you decrease the bias, but you increase the variance. Okay, you increase the variance. So what is the right level of model, and how do we decide what is the right level of model? This was a nice one-dimensional problem. We plotted it. Our final goal is to always do this 40-dimensional problems where we can't do this kind of plotting. Is there a way to analyze this and decide what is the right level of complexity we need to keep? That's the question we are trying to address. Okay, now in this case, that particular problem, this was the model we fit, right? But the way we solve any of these complex higher order polynomial problems is by replacing x square, x cube, x3 as x1, x2, x3, calling it as multi-dimensional linear problem. That's the way we solve it, right? So the question that we are asking is actually a more general question. For any multi-dimensional linear problem, how do we know how many features are important, what is overfitting, and what is underfitting? How do we know if we can drop off some of those features? Okay, it's irrelevant that some of the features in this case was x square, x cube. The point, the broader point still stands, right? How do we decide which ones to pick? Regularization is a way that helps you make this particular decision. Okay, the simplest models would be one where you maybe choose only one of the variables of all the 40 of them that are available. If you can model with one of the variable and set all the coefficients, rest of the coefficients to be 0, that will be your ideal model. That will be a very simple model, right? But the problem with that simple model is the error will be really large. So is there a way where I can play with the magnitude of the coefficients relative to the error that it might come out? That's what I want to do, and that's exactly how the regularization problem, how the regularization is done. Simple linear regression. What did we do? We computed the errors, yi, actual y points that were given, minus the forecasted yi, which is a summation of coefficients beta value times x value, right? That was the summation, the linear, simple linear this thing. The difference between them, square of that difference. This is what our sum of squared errors was. What we did was we found a beta value which minimized sum of square errors. Agree? We found the coefficient value which minimized sum of square errors. That's what we did in linear regression, which is why we call it as least squares regression, right? What we are going to do now is slightly different. We still want to keep the error. We want to make sure that the size of the error is small. But we also are putting a condition that I want to make sure that the size of the coefficients is also small. Okay, the coefficient can be positive or negative. Okay, if I just simply said I want the coefficient to be small, it will try to make beta values to be negative, which is bad. I want to set them to 0 if possible, right? So the way I say it is, I say take this error plus summation of all the beta values, the square of all the beta values. This combination together I want to be as small as possible. That's what I'm saying. Okay, that's a new condition I'm going to give. Now, previous condition when I did linear regression was only that factor. I cared only about the errors. But now I want to penalize complexity. The way I'm penalizing complexity is by saying that when the size of the coefficient is large, even though the small error is small, this coefficients are large, so my value might not be minimum. I want to minimize the overall, the joint effect of both of them. That's the way I'm going to phrase my problem now. Do you see the motivation as to why I'm trying to do it? I want simplicity. So I'm trying to put in simplicity, by saying that the size of the coefficients, individual coefficients, I want it to be as small as possible. Make them 0 if you want. Okay. So it's not just I want to minimize error. I want to keep the size of the coefficients also as small as possible. That's what I'm trying to phrase with this. Yeah.
So what is the correlation between the complexity and the beta value versus complexity?
Sure. So the correlation between complexity and beta value is the following. If previously we saw when we just minimized it based on sum of square errors, I'm trying to do sum of square errors to be as small as possible. It chose fifth order polynomial. So beta 5, beta 3, beta 4, beta 3, beta 2, beta 1, all of them are non-zeros, and it tried to make sure that the error is very small. But it resulted in this crazy little curve. I am saying that's because the focus was only on error. Now I'm saying I want the beta values to be as small as possible. I want the error to be small and the beta value. Make them 0 if possible. Okay, if you can do a better job with cubic fit, then make fifth order beta 5 to be 0, beta 4 to be 0, and play only with beta 3 if possible. That's what I'm saying. So I'm penalizing the number of terms. Okay, I'm penalizing the magnitude of beta as well. How many terms are there, and hoping that some of these betas it will put 0 while in the process of trying to minimize the combination of both of them. I don't care that it's penalizing only higher order. I'm happy if it does only fifth order coefficient, only x to the power 5, but rest of them are all simple. That is also possible. I'm happy with that. That's again a simpler equation, right? But that's because we're thinking only in the polynomial term. Equivalent to in the multi-feature one, I don't care if it picks only the fifth feature. If it sets all the remaining 39 of the features out of 40, it sets them to 0 and picks only fifth feature, I'm happy, right? I'm allowing it to set others to be 0 and pick only one if that is going to minimize this entire thing. Previously, I didn't talk about the size of it. So it chose whatever size, minimized only the error. But now I'm explicitly adding the size of it. Yeah.
These conditions, right?
Yeah.
So we put both of them mathematically and we put it together with plus sign.
Right.
Conceptually, those are separate.
Very good. Excellent. So the objection is actually even more fundamental. Objection is the same problem as before. What is beta? Beta was a coefficient that multiplied x, right? So the unit of this beta 1 is y divided by x1. x1 might be miles per gallon. x2 might be the size of the waist of the guy who is driving. Some other number. So beta 2 will have a different unit, beta 1 will have a different unit. Each one of them will have a different unit. How do I even think of adding them all together or the square of them together? You know what? I cannot add them if I don't standardize. So before any of the problem starts, you standardize all of those variables. Make sure that all of them are in the right units. Once I've done the standardization, this is a unitless number, right? And then all of these are unitless numbers.
My question is not that. I can find a number sigma beta multiplied by lambda.
Yeah.
A set where I have a sum of square errors is bigness. My business objective is to have this model with SSE small. But SSE could end up with a big number, but when we add up with the summation of betas, it will come to a minimum value. So my business purpose is not solving.
Right. So excellent question. Did you understand this question? The question was this. His claim is that your business objective has got nothing to do with beta at all. Business objective is to try and get as small an error for your fit as possible. That's your business objective. So why am I even worried about the beta? Fair question. The reason why we need to be aware of the beta is the true business objective is not to try and get as low error as possible in the training set. That was not your business objective. The business objective was how low error can I get on the test set. Test set we can't train. So, but we have this notion that if I focus only on the error in the train set, I can end up overfitting and get huge errors, as happened in the fifth order polynomial. So one way to account for that final business objective is make sure that none of the components are small, none of the components are too big, and try to keep the model as simple as possible. That is something that we have learned from experience. Every time you try to overfit on the train set, your test set data gets really bad. So I want to penalize overfitting. I want to use as less number of features as possible. I am imposing that by this particular constraint, by this condition. Good question. What is lambda? Okay, lambda is a number that you are going to choose based on how important is it for you to have a simple model. Okay, when I set lambda to be 0, then this becomes only sum of square errors. It will give you the same answer as the normal least squares problem. Okay, if I set lambda to be really large value, 1 trillion, really large value, then no matter how much hard the algorithm tries to fit this, the size of the coefficient will overwhelm this entire thing. So you know what the algorithm will do? Set all betas to be 0. That's the only way to minimize this thing. And it will set all coefficients to be 0. That is the simplest model you can think of. Use no coefficients, only the mean of the final y value is the best model. That is completely going towards simplicity, one end of simplicity. The other end is do not worry about simplicity, focus only on sum of square errors. So different values of lambda allows you to go explore different regimes. When lambda is 0, you are focused only on sum of square errors. You don't mind complexity at all. You worry only about sum of square errors. When lambda is infinity, you worry only about simplicity. You don't care about how well the fit is. I want only the simplicity. So it allows you to pick which one is more important for you. Relative importance of two models. That's a parameter that one needs to choose. Okay. How do we choose it? We'll come there in the next steps. Yeah.
Another approach we have there in that plus lambda times t.
Lambda times?
T is the total number of
yeah.
terms. That also could be minimized to get a simple.
So then when you choose the total number of terms, then you are here what you are trying to say is so there are a couple of ways of doing it. I'll address that when I show you the next way of doing it in a second. But do you one thing I want you to get at this point is that we are introducing a new term for our minimization problem. We are modifying our original minimization problem slightly, and we have put in a parameter which will tell us how important this new term is for our particular business case. Yeah, you had a question.
This process is trying to minimize beta values, right? Simplify the whole model. But would it guarantee that it also is reducing the overfitting problem?
Very good question. Would it guarantee that it will reduce? I mean, we are doing this to try and reduce overfitting. Will it actually do it? We'll come there. We'll see whether it does or not. But the intentions are pure. This is what we are hoping. Whether intent turns out to be good or not, good action or not, we'll find out. Yeah. So this process is called as regularization. The reason for that particular term will be understood in the next slide. Okay. So this is actually our way of coding this idea called Occam's razor. This is a concept we talked about earlier. Occam's razor is this notion we have in modern way of doing science is that the simplest models are better when two models explain this given phenomena equally well. The simplest model is more stable, is probably closer to truth than the more complex one. And the parameter, by putting in this additional term, we are forcing the model fitting to consider simplicity in addition to just errors. That's what we are trying to code it. Okay. Now the thing is, linear regression, what did we do in linear regression? We have y1 is a1 x1 plus a2 x2. Let's say we are doing two-dimensional linear regression. Okay. Y2 is, I don't know, a1. This is a different x21 plus, different values are there. Let's say you had only two records. Then this will be two equations. What are your unknowns? A1 and A2 are your unknowns. Two equations with two unknowns, you can exactly fit it. Correct? Two equations with two unknowns, you can exactly fit it. When you have a three-dimensional equation and you have three records, again you can exactly fit it. You can fit it with zero training error. In general, when you have n unknowns, n variables, n features and n records, you can exactly fit the problem. Okay? What happens if the number of equations you have is less than the number of features? What happens then? Remember from basic algebra, you have three unknowns and only two equations. Three unknowns, two equations. Can you solve it? What does that mean? We can't solve it. What do you mean by that? It means there are infinite possibilities for your unknowns. It doesn't mean you can't solve it. I'll be able to give infinite different solutions for the same particular problem, right? Like if I have an equation 3 equal to 5a plus 2b, I can give you infinite prescriptions for a and b which will satisfy this equation. So when n, the number of features is larger than the number of data points, linear regression will fail because there are infinite possible slopes. It can't figure out the answer. This is not a random problem. It happens in the area of genetics. The number of features that you have is huge. Number of records you have will be small. And this is again, is there a way we can find the best set of coefficients? Well, actually, unfortunately, linear regression will fail. You can't do it. It will also fail when you have perfect multicollinearity. We did this example. If you remember this data set, y, x1, x2, 0, 0, 2, 1, 1, 4, 2, 2. What is the equation for this? We talked about this. It can be y is x1 plus x2, or y is equal to 2x1, or y equal to 0.5 x1 plus 1.5 x2. Any of those are possible solutions. When you have perfect collinearity, linear regression will fail and you get a slope of NA. All the slope coefficients will be NA. Linear regression fails in perfect multicollinearity. This kind of thing is called as ridge regularization or ridge regression. By adding this extra term will allow you to solve that equation perfectly. Why? And it will also explain why the ridge coefficient comes. What we are trying to do when you are doing linear least squares methodology for this kind of problem is that for any value of slope coefficients, arbitrary value of slope coefficients, you plot the error.